All right, so question 3 was by far the most annoying problem on this worksheet, and I think, but we'll go through it together, and I think with some of the hints that I can give you, I think it'll be a little bit better. But not gonna lie, it was pretty annoying. So let's read it through together. So a surveyor standing 50 feet from the base of a large tree measures the angle of elevation to the top of the tree at 71.5 degrees. How accurately must the angle be measured if the error in estimating the height of the tree is to be less than 6%? So I went ahead and tried to represent that schematically. So I'm imagining the surveyor standing at this corner of the triangle and the tree being the opposite side of the triangle. We know that the distance from the surveyor to the tree is 50 feet, and it's gonna really help me to give a name to that angle of elevation. So I'm gonna denote the true angle of elevation to the top of the tree as theta. So that's gonna help me out. And once I've done that, I know that in that case, the true height of the tree should be 50 tan theta. So we're going to name that angle theta, and then I know that the true height is going to be 50 tan theta. So that's essentially the first line over there. And then what else is going to help me is to denote the error in measuring theta. So I'm going to call alpha the error in measuring that angle theta. And once we do that, then the measured height is going to be 50 tan theta plus alpha, right? Because alpha was the error in measuring the angle. And so the measured height is going to be theta, tan of theta plus alpha times 50, just like the true height was 50 tan theta. All right. And then it just immediately follows that the error in the measured height is going to be that difference, right? It's going to be 50 tan theta plus alpha minus 50 tan theta. So the question tells us that the error in the measured height, so that difference, has to be at most plus 6% of 50 tan theta, or at most minus 6% of 50 tan theta, right? So either we overestimate by 6% of the true height, or we underestimate by 6% of the true height. So think about that for a second. Okay, so once you feel comfortable about this inequality, let's go cancel out those 50s so it simplifies a little bit. So I'm dividing throughout by 50. And the next thing I'm going to use, and this is like the really big hint here, is that we're going to be allowed to approximate this difference using a derivative. So just because of the definition of what a derivative is, from that definition, if alpha is really small, then alpha times the derivative of tan theta is going to be a good approximation for tan theta plus alpha minus tan theta. Okay, just from the definition of a derivative. So my next big hint is that we're going to use this approximation. So we're going to use the fact that this difference here is approximately alpha times the derivative of tan theta. So once we're doing that, then we know the derivative of tan theta is secant square, and so immediately we know that that difference is alpha secant square theta. All right, so I'm going to replace that difference there. So I'm going to replace this difference up here. I'm going to replace this difference up here with alpha secant square theta. And then I divide by secant square, and that's giving me this expression. So I did a couple of steps there. Take a few seconds to see if you follow. So I first replaced that difference with alpha secant square theta, and then I divided by secant square theta. All right, next I simplified a little bit, and that tells me that that gives me this expression. And then in the next step, the next step is totally optional, but I thought it might help at least in explaining or while explaining this problem. And I replaced sine theta, cosine theta by, basically I replaced this by half sine 2 theta. So I replace it by half sine 2 theta on both sides, right? So I replace this guy by half sine 2 theta. And this step is totally optional, but then it gives me sort of a cleaner expression, the one I have down here. All right, and the next hint I'm going to give you is that we're going to approximate sine 2 theta, where theta is a true angle, by sine of twice this angle that the surveyor measured. So that's my next hint. We're going to approximate sine of 2 times the true angle with sine 143. And then you can just plug in and you'll see that alpha must be, your calculator is going to tell you that alpha must be between plus or minus 0.018 radians. And that's that. That was super annoying, but hopefully this explanation makes some amount of sense.